Thank you for coming to the last session of the day and not just going off to have a beer. I really appreciate it. A caveat before I start. I'm just getting over a cold. I'm using a handheld mic so that I don't cough on you all, and or at least I'm going to try. I will forget I'm using a handheld mic, and I'll just walk away from it. When I do that, remind me that you can't hear me. Okay, so I want to start with a question. What would happen if all of the machines you run on, every single one, whether they're in the cloud, they're in a data center, or they're under your desk, they all restarted right now? Like, sure, you'd have an... You're quiet. Well, that would be good. Sure, you'd have an outage for the duration of the reboot, which is like 2 minutes or whatever. How much longer would you be down? I'll leave that question with you. So hi, my name is Tanya. I'm a site reliability engineer at Google working on low-level infrastructure and dependencies. And I usually say I work at the bottom of the stack. So what does that mean? I had this great conversation about that once. I was giving a talk at New York University, and afterwards this one student came up to me, and she said, "What can you tell me about Google CMS?" And I said I was sorry, but honestly I didn't know. I've been doing infrastructure things for more than a decade now. I don't know anything about front-end stuff. She said, "Oh, sorry, I mean content management." And I'm like, yeah. And we just stand there looking at each other for the longest time, like, what is the language difficulty we're having here? And so, I mean, bear in mind, she's maybe a second-year student, and I've just spent 30 minutes talking to her class all, I am bringing great wisdom from the industry, or whatever. So kudos to her for pushing on with this and not just running like hell. But eventually she said, isn't the CMS the back end? And I was like, well, yeah, sort of, kind of. You're not wrong. It's just, I'm further back than that. And her eyes went really wide. And I swear she said, there's further back? So it turns out everybody's back end is someone else's front end. It really depends on where you're standing. There's this parable in various Hindu, Buddhist texts about trying to identify an elephant by touch. You're going to have a completely different idea of what this thing is, depending on where you're standing. Someone's going to be like, oh, it's like, you know, it's kind of like a wall, or it's kind of like a spear, or, you know, it's kind of like a snake. I mean, it's the same with our systems. It's a front end, it's a back end, it's a platform, it's a user, it's everything. It's all of these things. It depends where you stand. So for all, I think of myself as being at the bottom of the stack because I care about machine installation and job control systems and what time everyone thinks it is. The core networking people are all, high up there. And the power and the cooling people think the same about them. And, below that, someone had to pour the concrete. But anyway, this story about where the CMS sits, I found so entertaining at the time. And I told it at a lot of parties, very popular at parties with this sort of story. And it took me a while before I realized that I had the point of the story completely wrong. So I thought that the point was that the really important infrastructure that I work on is just bigger than people think. The stack goes down further than you think. And that the student just hadn't learned about how complicated infrastructure is, and isn't that cute? But that was wrong, because it turns out it is just as wrong for me to split the world in two, the parts of the world that I know, and say that everything that's above some height is the front end. That's not more wrong. It's not more right. It really depends on where you stand. Increasingly, our stacks are really, really complicated. When we're talking about all the systems through hardware and power and networks and infrastructure and processing data and applications and user-facing stuff and client-side, unless you have the simplest site in the world, nobody knows it all in depth. I think probably even if you have the simplest site in the world, nobody knows it all in depth. We know the tech that's adjacent to us, but we make abstractions to make sense of the world. We just can't function otherwise. So here's a model of everyone's stack. There in the middle, that's you. That's your system. Above that, you know your system. Above that are your users. Whoa, microphone. Above that are your users. You know what they're doing with your system. You don't know what they're doing with your system. Users are really resourceful, but you like to think you know what they're doing with your system. Below that, your direct dependencies. you probably don't really know everything else. And that's okay. I mean, that's society. That's a societal model. We humans specialize. We go deep, right? I mean, most of us don't really know how water gets to our house, or how twisty light bulbs work, or where breakfast cereal comes from. Like, really, where does it come from? We don't know this. But that's okay. We can trust that these things will continue to flow to our house. It's the social contract. And it's the same with systems. We make social contracts, or even formal SLAs, with the people below us in the stack. And that informs what social contracts or SLAs we can offer to the people above us. But in a disaster, this societal model, it fails us in two ways. One is that as much as we trust that our electricity and our water will continue to flow, we might also keep candles and bottled water in our house. We need to know a little bit about how to make light and how to have water. Because sometimes the things lower than us in the stack can't fulfill their promises. And we just have to know something about them. That's the fallback plan. And the other is that these things that we depend on, they might depend on us right back. And we could have a bootstrapping problem right there. I love this tweet from Zeynep Tufekci. Huddle around the fire, children. I'll tell you how interdependencies and complex couple systems took it all down. Eat your cockroaches. Can interdependencies and complex coupled systems cause our entire society to fall and not be able to get back up again? Maybe. This is a topic that I love debating over beverages, so come find me afterwards if you have strong opinions on it. Can they cause a site to be unrecoverable after a disaster? Definitely. So I'm going to talk about three things today. First, more about fallback plans, why they're inherently dangerous, and why they break the societal model so we don't get the nice, clean abstractions that we would like to have. Then I'm going to talk about dependency cycles and bootstrapping, and how not globally managing our stacks can get us into trouble and make it really hard to recover after a disaster. And finally, I've got solutions for both. Fair warning, I'm going to try really hard to convince you to start managing your dependencies now if you don't, even if you're too small to manage your dependencies, especially if your site is too small to start managing your dependencies, because you have a better chance of succeeding. Let's start with fallback plans. Okay, fallback plans are the things we do when our regular operations aren't available. Like anytime we think about what would happen if something went away, how will we deal if our database is briefly unavailable? That's a fallback plan. What if our entire site goes away? Are we going to fail over? That's a fallback plan. There are things we don't want to do, and there are things we don't do very often, and that means they're a little scary. Some examples of fallback plans, like serving from a cache of last known good data, or starting up with a different config, or recovering from tape, or starting up the backup generator, or getting a key from a fire safe. There's stuff that they're not what our code or our services or our humans usually do, and chances are it's been a while since we've done them last. And that means that fallback plans are the scariest and most precarious pieces of our infrastructure. When we do need them, they're the last resort. Like, they really have to work or we're in big trouble. But by design, they're not used very often. So you're doing something not very well tested, and it's quite likely to hide weird edge case bugs that you just haven't stumbled across yet. When your infrastructure is changing very fast, it's hard to be sure that the fallback plan that worked in the past will still work. Like, maybe this thing was completely badass and worked great, but you had a 10x increase in user traffic, and it doesn't work anymore. So I want to talk about the perils of the fallback plan by looking at two common fallback plans that will apply to many people here: backups and DR sites. Backups. You take a copy of your data and you put it somewhere else, hopefully further away than the same machine. My friends in Google's data integrity team say, you don't need a backup plan, you need a restore plan. Because there are some ways it can go wrong. So I was telling a friend about preparing this talk, and he was like, oh yeah, funny story. He had just found out that he'd been backing up his database for years with file system snapshots. He just found out that the database kept some state in memory that mapped the tables to inodes on the disk. Without that metadata, the backups were completely worthless, complete garbage. He'd been doing it for years. Untested fallback plans, they're a gamble, and they're not a gamble you're necessarily going to win. If you haven't tested you can recover your backups, you don't have backups. And I mean more than checking that you can get your data back. I think that's not that controversial anymore. I'm not going to ask for a show of hands because it's kind of embarrassing, but people test their backups, right? So people aren't, I was going to say not that much nervous laughter, so this is good. But you've got to test more than that the data comes back. Like, if you can get your data back, but you haven't backed up the decryption key, hopefully you don't have backups. Hopefully that's going to be hard to recover. If the data is in some proprietary format and you don't have a license to reinstall the application, you don't really have backups. If you have incremental backups, but you can't backfill incremental data, or if you have full backups, but you don't have enough network bandwidth or disk to get the data where it needs to be to use it, or best of all, if you can recover from backups, but it will take so long that your customers will stop paying you, your company will go out of business, everyone will lose their jobs, and it doesn't matter that the data is there, you don't really have backups. But you got to test them, but Fallback Plan's bit rot, so you can't just test them once and call it good. And testing backups is incredibly tedious. It's the sort of thing, you do it and you say it's done, and it's like you just don't want humans to do this. If your fallback plan relies on human willpower, it's already failed. Humans are terrible. So your recovery tests need to be automated. You really need robots to do this, or it's doomed, and then you don't have backups. But most of the time we want to survive more than a data loss. We want to survive the loss of an entire site. So a lot of people, a common pattern is to have a DR site, a failover site, just sitting there waiting to be failed over to. And this is a great illustration of the anti-patterns in fallback plans, which I'm going to illustrate by asking 3 questions. And I invite you to consider them while thinking, hold in your mind a failover site or a different fallback plan that you know and love. Question 1, and we have to be honest, is it kind of a decoy? I mean, did you build this thing because some VP got nervous 5 years ago, and they said you had to, but no one really had time to make it solid, and it looks kind of like a real site from a distance, but it's not really. A fake plastic DR site, it's kind of worse than no site at all, because it gives you a false sense of security. It's a social contract. If a DR site exists, people will assume they can fail over to it in an emergency. If it's not real, at least tell people, and then they'll make some alternate plan, rather than waste time. Question 2, is it bit rotting? It is definitely bit rotting. How badly is it bit rotting? If your sites are managed by perfect robots, then you have some chance of keeping it up to date. But most likely you employ humans, and humans are terrible. We add things, we change things, and we don't think of making sure that it works in DR. If you need to be able to lose your entire site, then everything has to work. Your authentication has to work, your config system has to work, your monitoring has to work. Everything has to be available in the old site. It takes work and serious processes to make sure that that's the case. The flip side of this is, of course, that you can be too up to date. Like, have you ever seen a database, a failover plan, a DR database, which is created by replaying every transaction to the primary database directly into the failover? So this is cool if the disaster you're protecting against is losing a site. It's completely up to date. But if the disaster is that somebody just pushed a schema change that blew away the database, you might wish that you'd left a little delay. Question 3. This image from my Pinterest board, apartments I would be terrified to drink red wine in. Question 3. Has anyone ever used it for anything real? And again, I'm talking about failover sites here, but really any kind of fallback plan. A fallback plan that isn't regularly used, it's not really a fallback plan. I know I said that about databases or about bad backups, but it's still true here. So yeah, you can test that you can bring up your development environment in the other side, and it seems to work, and everything is good. But can you restore keys to there? Can you actually run out of there? Can you recover the data? And the bit that I found funny is how many requests will it send back to hard-coded addresses in your primary site while it's happening? Until you've failed over and back a bunch of times and actually firewalled off or switched off your main site, you've got to assume that something's missing and it doesn't work. Another story, I love this. I've got a friend who works for a big online clothing company, and it usually ran out of the east coast of the US. And they tested, thank goodness they tested, failing over to their other site on the west coast. Now, all of the machines on both sides were in local time. So the database started replaying transactions that were in the future. The database did not like that. It refused to have anything to do with it. It was just like, nope, come back in 3 hours. And this is why we do disaster failovers before we need them. Okay. But this is the LISA conference, and we're 2017. So many of you people are like, DR sites, are you from the past? I have tons of completely replicated sites. If one failed, I would elegantly drain and redirect the traffic. Look, I will do it right now from my smartwatch. The best fallback plan is not needing a fallback plan, so this replicated future is awesome, right? So, we move traffic around anyway if we have a lot of replicated sites. And in that case, we can lose a site, and it's just a regular capacity problem. It's just shunting traffic around. It's no big deal. And there's no bit rotting, because everything's in use all the time. It's one of the beautiful ways that our systems are more resilient than they used to be. But it doesn't mean that you don't need to think about disasters and failovers if you're replicated. And this is because dependencies. So I kind of just had my thunder spoiled because I was going to talk about something you may remember vividly and possibly vividly and late at night when someone deleted a module from NPM last year. That's a build time dependency, and it's not what I'm talking about now. I really just mention it to make people feel sad. But I'm not talking about build time dependencies. I'm talking about real-time dependencies, runtime dependencies. Systems that can't start or can't run unless another system is running. We have a lot of these in the microservices world. And they mean that we can't think about and replicate systems in isolation. Let's look at an example to be concrete. Say you've got two services that both need a currency converter. In olden times of 2 years ago or whatever, you would bake a currency converter into both of them. Or maybe you'd even, you'd maybe use the same library if they're in the same language. But now, it's more likely that rather than have to keep them both up to date, you would set them up to send their currency conversion requests to a third service. Now, only one thing has to care about exchange rates and currency conversion logic and so on, and the other two just need to know how to talk to it. And so they're talking to it over, there's a bunch of popular approaches like JSON or protobuf over HTTP or Apache Thrift. And Google, we have gRPC, and we use a version of that internally. So what's interesting about these dependencies is that most of the time, we're not writing network code to talk to them. It would be kind of weird if we were. Every time the sales service wants to talk to another dependency, like the currency converter, they're really explicitly saying, I would like to make a network call to that. Maybe a little bit in the RESTful world. But a lot of the times, that's done once, and it's wrapped in a library. And then you use the currency converter library. It's very easy to forget that there is a request going over the network to another service. So you might not think of it as an external dependency anymore. And the more you decompose your services into microservices, the more dependencies you've got to keep track of. There might be a lot of them. I like to look at big distributed systems as graphs with nodes and edges, where the nodes of the graphs are the individual running binaries, or even running groups of binaries and services, and the edges are the dependencies between them. And those edges are where all the action is. It's where the really interesting failures happen. Over time, the libraries you use, the dependencies you use, they can change over time. The services that you do know you depend on can change their implementation, and they can start depending on stuff that you prefer that they didn't. You can pick up new dependencies that you don't even know about. Equally, remember, your service is a dependency too, and so you can pick up users that you don't know about. Again, you don't know what your users are doing. They're really resourceful. And they may think that you're offering more reliability than you think you are, especially if you're running a stable service. Stable services get things built on top of them. And you may think of yourself as a not very important front end, but someone else may think of you as a critical back end. If you don't know who your users are, you don't know what reliability they expect of you. And if you don't know what your dependencies are, you don't know what reliability you can offer to them. Unexpected dependencies can be a source of outages. A service cannot be more available than the intersection of its critical dependencies. If you don't know you're using some system, then you're not designing for its failure. And all of your SLAs are lies. But even more than that, you need to know your dependency because of the place in the stack, because of the social contract. It's society. You owe it to society. And that's because everything I said at the start was a lie. Not only is there no front end and no back end, but there is no stack. These are lies we tell undergraduates. In most sites, what there really is, there's a deranged tangle of things that grew organically in whatever way was convenient for whoever was designing the system or writing the code at the time. The deranged tangle is really hard to deal with day to day. It decreases your velocity, but it's especially hard to deal with in a disaster. Because when we plan disaster recovery for a site, we plan it in the same little sections that we operated in. We practice testing and recovering the parts that we know, and we assume that everything above and below will just keep existing. And again, that should be reasonable because of society, but dependencies make it all fall down. Like, when systems get really big, it's hard to reason about them. So, system A depends on system B and can't start without it. System B depends on system A and can't start without it. Those two groups of people will probably notice. But if A depends on B, which depends on C, which depends on D, which depends on A, you might not notice that until you're trying to turn it all back on again. The worst cycles, the most exciting cycles, are the ones you can't recover from. The ones that remove your access to the control plane of your service, like this one. For example, maybe everything is blocked and waiting on the network, and there's a network device that's wedged, and you know how to unwedge it, but you can't get to it because the network is down. Or maybe you've made a bad config push, which makes it impossible to make any changes to your config system to make a good config push. Or your IP addresses have changed, and you've got the old ones hard-coded, but you can't change them because the build system depends on the old IP addresses. Or maybe your startup process is incredibly arcane, but really, really well documented, very faithfully, carefully documented in the documentation server, which you don't know how to start up. You can get really badly wedged and be unable to recover. We can think of huge interdependent computer systems as machines. Like, I like to think of it as, a big weird machine assembled over years or decades by people, like lots of people who didn't know each other. And we just, as we increase the complexity of our systems, we just bolt extra pieces onto the outside. Occasionally we deprecate something or replace it, but it mostly gets bigger and more complicated. We build it once, and then we expect that it will just keep running forever. Some part of the system will always be running. A metaphor I've heard and liked is like, we're like cave dwellers who don't know how to make fire, but we can start a new fire by taking a torch from the last fire. But what happens when the last fire goes out? So here's that thought experiment again. Every machine you run on restarts right now. I hope you're saying, by the way, that can't happen because of separate failure domains. But humor me for a moment. Are you certain that your systems, your sites, your machines don't share anything that could cause everything to reboot or restart, or get wedged or compromised in a way that means you have to restart them all at once? Like, could they share a power supply manufacturer, an OS version, a low-level library that might contain the word halt, an authentication system, a config push mechanism, an operator who's really bad at scripting, an operator who is incredibly good at scripting and hates you? A global restart can happen. If it did, how long does it take you to be back to normal? Like, let's imagine that this is the luckiest day of your life and every single thing comes back and there are no hardware failures. If you're running a 4.9 service, you get 4.38 minutes of downtime per month. And your machines can reboot in, like, how long does it take for a Linux machine to come back? Like 2 or 3 minutes? So you're golden, right? In an ideal world, yeah. But in a real world, you may have something like this, where your front end sits there waiting until your storage is available, which is a reasonable way for a front end to behave. And your storage sits waiting for your encryption keys, as it should. And the decryption is waiting for the authentication system to make sure that it should decrypt, which is fine. And the authentication system is using keys that are stored in the storage. So these 4 systems are all sitting there waiting for someone to tell them what to do. At the same time, the job control system would like to pull data from the config system to know what binaries to run. But the config system's trying to do a master election, so it's got to call out to the consensus system. But the consensus system wants to make sure that it's got up-to-date software, so it's talking to the service registry, which is supposed to be running on the job control system, and it's frantically pinging that to ask if it can run now, please. And the job control system would like to make sure that it's even safe to start, so it would like the authentication system to reply already. You're stuck. In a disaster, all of that will sit there forever until a human figures out how to break the deadlock. But it doesn't have to be that way. We can prepare for disasters and for bootstrapping. We can run systems that are both more reliable day to day and are more possible to restore in a disaster. We can do this by managing dependencies and by reducing the need for fallback plans. So the first step in dependency management is finding out what depends on what. Some folks know, some people, it's a delightful surprise. But like so many other things in SRE and systems administration and systems engineering and whatever else we do, it starts with monitoring. So just gather the information. You might not like what you find. When we started doing this, we had a lot of conversations along the lines of like, oh no, your system is wrong, we don't depend on that. Oh, we do? We do depend on that? Oh, why do we depend on that? Ooh, we shouldn't do that. So I want to show this in action, collecting dependency data for a very important made-up application that displays pictures of cats on the internet. You know, you got cats, you got people who want to see cats. It's like, you want to serve the right cat. So here is a made-up snippet from a made-up design doc that you should not use to implement anything because it's nonsense that I made up on the subway. Okay, first design doc. We keep an in-memory index of the cats with some metadata. The cat chooser uses the information to determine the attributes to fulfill. It checks the index for cats that match the attributes, pulls the cats from storage, returns a cat, probably a cat picture, not actually a cat, to the user. Indexers run at start and at intervals to update the metadata and make sure we have accurate cat sentiment analysis and geolocation data. This stuff is important. You know, you go looking for a picture of a happy cat and you get a sleepy cat. It just ruins your whole day. But then, so this is wildly successful. And everyone loves it. And then the product manager files a P0 bug. Oh, we are occasionally serving pictures of raccoons, and the users hate that. So you've got to add another component, catness analysis, obviously. So here's a snippet from that design. Catness analysis is an expensive operation, as I'm sure everyone knows. So we only run the catness analyzer on pictures that have a high likelihood of being served, i.e. those already indexed with geolocation and sentiment data. So we take the index from the cat chooser, we run catness analysis over the cats from the queue. So, right, this sounds awesome, right? I mean, bring on the cat analysis. But if you have a way to discover the dependencies, you get to see if this vital application is safe. Here's the dependency list. It says like the web server depends on the cat chooser and the cat chooser depends on the geotagger or whatever. And this is better, but it's still hard for a human to reason about. We need pictures. There's lots of good ways to make dependency graphs. Like Netflix has this visualization tool called Visceral, which is really beautiful. But most of the time I use GraphViz. Look at this. This becomes a GraphViz graph. Isn't that amazing? I love GraphViz. So excuse me for a moment while I just go on about how great GraphViz is. But let me work through the complicated config here. Digraph means put arrows on your graph. Everything else is the dependencies. There's the command line at the top. You've got to install the GraphViz package if it's not already installed. Humans can deal with this now. Humans can say, what's the deal with those two arrows between the cat chooser and the catness analyzer? If we restart them both at once, does that mean we'll take down all of the cats? That would be really bad. GraphViz has millions and millions of options. I made nearly all of the pictures in this slide deck with it. And I'll link to my GraphViz picture GitHub repo at the end, so I can tell you some more about how great GraphViz is. There are definitely fancier and more elegant ways to draw diagrams, but this is super fast and you can do a lot with it. Anyway, where does this data come from? In this case, we mined a design doc, but that doesn't scale because you have to parse text, and parsing text is hard because humans are not good at that. There's a lot of things we're not good at. Humans are basically terrible, but mostly it needs to be programmatic. You want a robot doing this for you. If a human is sitting down drawing lines from box A to box B based on what they remember, it's going to be wrong. We're sort of lossy for this sort of thing, right? So what robots do you have that know what's going to what? Like maybe your monitoring system. Maybe you can add code to your common libraries that will continuously export this information in some way that you can monitor. Maybe network devices, load balancers, or service mesh, or a name resolution system, or running queries over standard logs. Something, or structured logs, something like that. If you've got standardized infrastructure, it's easy, and if you've got a mix of everything, it's going to be harder. But you probably have a mechanism for finding out what's talking to what. But one thing you should be noticing and objecting to in all of this is that all of those mechanisms are after the binaries are already running. Like you won't see the cycles until after they've happened, and it's a bit late at that point. So ideally, you want to prevent them from happening in the first place. And we can do that. I mean, we can set rules for what can talk to what. And my advice is to lock this down earlier than you think you need to. Because people, when they're designing something, will see that another system exists somewhere, and they'll just start using it. We've got no self-control about this sort of thing. Nobody stops and says, is this a safe thing to depend on? It's like, well, it's fast, it'll work. Distributed systems rarely get simpler. And, they'll grow, and even if you don't need it yet, set some basic rules about what can depend on what. Communicate what's normal for your stack, and don't make people reason about it every time. So, some things, it seems it's probably not controversial to tell people your authentication system should not depend on your front end. Like they'll probably think about that. But when is it okay to use DNS? DNS is a real dependency, and it's not as low in the stack as we sometimes like to think. Like, it's just we just throw out a system call, and it mostly works like magic in the background. So we kind of think of it as free. But where do your DNS records come from, and where do they go to, and what would happen if it's not available? DNS is a real dependency. Anyway, write a bunch of policies. Make your design documents, or however new systems come into existence, assert that they have followed the policies and list their dependencies. But even better than policies, if you can, make it actually impossible for things not to be able to contact stuff they shouldn't. So the way we did this was we built it into our internal version of gRPC, into our remote procedure call library. It's my team made this. It's really cool. So it's kind of like an access control list, like an ACL, but in reverse. So rather than saying, can other systems talk to me, we say, should I make this system? Should I make this call? We check if it's an expected dependency. And the way we do this is we roll it out in monitoring mode first. So it'll still send the RPC, it'll still send the request, but it'll increment some monitoring data and make sure that you find out about it and maybe get paged about it or open a bug to say, do you know you depend on this thing? But later we flip a flag where we just drop the request, we drop the RPC, which works well, and it encourages people to have very good canaries. If you use Kubernetes, you get something like this for free with the Network Policy API, which went GA this summer, which I haven't used, but it seems very cool. And I think Istio can do something like this as well. If anyone knows of other implementations of it, of this sort of thing, I would love to hear how other people are doing it. Because when we did this, we couldn't find a lot of prior art. We don't know how other people are managing dependencies. And I'd love to see what else exists out there. So yeah, give me a shout on Twitter or come find me afterwards if you're doing this. Again, maybe you think your site is too small to do this. Believe me, if I could go back in time, I would have us do it way, way earlier than we did. Like in 1998 when Google was founded, I would be like, nobody can depend on things they shouldn't. They would be like, what? Because it's trivial if you start when it's small. It's just when you can reason about it. When one human can reason about the whole system, this is a great time to start thinking about what should depend on what. It is, just trust me on this, it's harder if you have to come back and do it later. So the other good thing about starting early is that then you can design your systems to be bootstrappable from the start. You can have this built in. And you can set some simple rules about how to architect systems on a model that is fundamentally bootstrappable, which is layers. Not OSI layers like rock strata, things on top of other things. So here's how layers work. You divide your stack into sets of things, each of which can completely start up and run without anything above it. So here's the first set of jobs. They can completely start up, even if the rest of the world doesn't exist. Here's the second set of jobs. They only depend on the first set of jobs, and so on, the whole way up the stack. And you could split it into network and infrastructure and application and user-facing, but whatever works for your site. And again, if you're feeling fancy, you can enforce this in code. And we're doing that now. So you could say, this low layer thing is contacting a high layer thing. We should expose that as monitoring data, or even block it. If that's rock solid and reliable, you know what you have? You have a stack, the mythical stack. It exists. And then if you have a stack, you can have a social contract. And if you have a social contract, you can go back to just knowing your own part of the world, which is very reassuring. People will try to break your stack. They will. One thing you'll come up against if you do this is the concept of soft or optional dependencies, where people will say, yes, we use that, but we don't depend on it. We can start without it. We can run without it, mostly. And people will argue that they should be allowed to go up the stack, and it's not necessarily wrong. It's not an unfair argument, but I would say mostly discourage it as much as possible. Every exception adds cognitive load, and it's an extra thing you need to test to make sure that it's actually a soft dependency. Like monitoring. it should be, you should be able to start without monitoring. But I've seen people build load balancing systems and health checking systems on top of monitoring. It might not be as optional as you think. It might have suddenly become structural. If you do this and you decide to allow optional dependencies, I recommend dropping the optional dependencies at intervals to see who screams. Just like, you said you don't use this, so I've taken it away. It's like, if they can't survive without it in a controlled outage, they can't survive without it. And they need to decide what happens if they go away. Which brings me back to fallback plans. So whether you're trying to recover from the failure of one server or bringing your whole site back online, the fallback plan needs to not have many moving parts. It needs to be the tightest, most tested, most badass procedure you have. And the fewer of them you have, the better. Because they're not the regular way you do things, so they need extra testing. My favorite model for fallback plans is the reserve parachute. If you're a skydiver, you don't get to decide what your fallback plan is if your parachute doesn't open. You carry a second parachute. That's the law. And you don't pack the second parachute yourself. It has to be packed by a professional. And you try hard not to use it. If you were packing it yourself, after a bunch of jumps, you might get tired, or you might get sloppy, or you might decide this one is going to be fine. Everything is great. No, you carry a second parachute. It's packed by a professional. You don't open it, and you do your best to never use it. But when you do use it, you can trust your life on it. Model fallback plans on that. Last thing, even with layered architecture, managed dependencies, and teeny tiny solid fallback plans, it's good to occasionally test that you haven't missed anything. Like, can you really restore the service if it goes down everywhere in the world at once? Or can you turn your company back on after a global reboot? Most of us can't turn our companies off and on again, though it would be really exciting, wouldn't it? But we do need to test. So it's worth doing occasional real-life disaster tests, mostly so that humans don't, if there is a disaster, humans have already done this once and don't freak out. But ideally, most of the day-to-day testing will be done by robots, who usually don't freak out on their own. One of the nice things about automating your disaster testing is that you can build tools to do it which are actually useful in a real disaster. Or even better, if you can make them actually useful day to day. That means they're not fallback plans. They're just part of your regular operations. A good test you can do is, if you're building a new site or moving to a new region or data center or whatever, can you use your DR plan to bring that up? Can you completely separate the new site off from your existing sites? And see if you're able to bring it up. How many times will you have to go back to your real site to get data or media or keys or passwords or binaries or people that you didn't expect to need in a disaster? It'll help you figure out what you need. So understand what you need, make sure everyone knows how to get it, and have it ready to go. But keep that as small as possible because it's a fallback plan. So it's bit rotting from the moment you put it into place. So I just said a lot of things, but if I get to have you take away anything, here are 4 conclusions I would like you to take away. One is, as much as possible, make your emergency plans follow a well-trodden path. So code and systems and processes that happen rarely, they're going to bit rot, they're buggy. It's the backup generator problem. You don't remember how to use it, and if you do, it probably doesn't work. Have a well-defined way you want users to react if something goes away. And a bad fallback plan is worse than no fallback plan. In case I haven't said it enough times, if you haven't tested it, it probably won't work when you need it. The middle of a disaster is no time to find out that you can't reinstall some app or you don't know how to get into your FireSafe. Even if you think your site is simple, understand and manage your dependencies early. At the very least, discover what they are, and ideally have some policies on what can depend on what. Make dependencies part of your design conversation. Have rules and be really opinionated about it. And protect yourself against future dependency chaos by putting a structure in place early for bootstrapping your system in layers. And again, do it before you need it. Push back on optional dependencies if you can in special cases. Make it as easy as possible for people to do the right thing, though. All of that can be summed up with the motto of Google SRE, which is hope is not a strategy. And it applies as well to disaster recovery as it does to a lot of things. And that's all I have. Thank you.